Okay, we're going to start our notes about standing waves. And a standing wave is a stable pattern formed by the interference of two waves, two identical waves, traveling in opposite directions. Okay, and I want to make a note over on the side over here that if I want to find a wavelength, one way to do it is think of a sine wave, and it's going to start to repeat itself over here. So this is one wavelength, like so. All right, now, our first type of standing wave we're going to talk about is what's called close both ends. And this works in stringed instruments. When it says closed, it means it can't move. So in a stringed instrument, the ends are fixed and they can't move, and the middle can. So like when you pluck a guitar string, the ends stay fixed and the middle vibrates up and down. So I'm going to make a couple definitions over here. A dot is what's called a node, and a node is a position of destructive interference. Okay? And there's going to be no amplitude there because of destructive interference. The waves wipe each other out. This little dotted line, where the amplitude is biggest, we're going to call an antinode. And that's where there is constructive interference. Okay? So this first standing wave is called the fundamental frequency or the first harmonic. And it's very easy to get something to vibrate that way. So when I pluck a guitar string, this is the way it vibrates. The biggest oscillations are going to be in the middle, and at the ends, it's going to be fixed. Now, I do want to make a note for this one that since over here a wavelength is like a whole sine wave, 360 degrees, in this first one here, I only have half of that. So the whole wavelength would be twice as long as the string. So I'm going to make a note that the wavelength of the wave is going to be 2 times the length of the string. And then our frequency for this one, we're going to call F1 our fundamental frequency or our first harmonic. Now, as you saw in the previous video, if I start to speed up a little bit, at first it'll get all jumbly, but then if I go just the right frequency, I can set up the next pattern, which is called the second harmonic. And what happens is I have the 2 nodes still at the end, but now I've added a node in the middle where it's going to be destructive and the string doesn't seem to move. And then we have antinodes, okay, here. So I have 2 antinodes instead of 1. So if they ask you to draw the second harmonic, you just have to know to add 1 more node in the middle. Now, this, from here to here, is 1 wavelength. I go up and then back down and then up again to the center point. That's a wavelength. So I'm going to say that our wavelength is equal to L. So from 1 to 2, our wavelength is halved. If our wavelength is half as big, that means that our frequency is going to be twice as big because wavelength and frequency are inversely related. So the frequency is twice the fundamental frequency. And Western music is kind of based on all of these different harmonics. If I double the frequency, I go from the fundamental to the first harmonic, that makes an octave. So if you study music, when you change an octave, say go from middle C to the next highest C, what you're doing is you are doubling the frequency. If I speed up a little bit more, I get a little bit higher frequency. Now I get the third harmonic. Again, I'm just adding another node. Instead of there being 3 nodes like in the second, now there's 4. If I think about it, the wavelength now is going to be this long. It's 2/3 of the entire length. So the wavelength is 2/3 of the length. If I compare that to the original one, which was 2 times the length, it's 1/3 as big. So the frequency, which is an inverse, is going to be 3 times the fundamental frequency. And so on. Okay, if I go down to the fourth harmonic, we can guess that the frequency of the fourth harmonic is going to be 4 times the fundamental frequency. Okay, and again, I just add one more node. So now I have 5 nodes. So the fundamental frequency has 2 nodes, and then as we go along, we're just going to keep adding nodes. Now, we can be open one end, and that would mean that we're closed on the other end. So sometimes I'll call this closed one end. Now remember, we said closed means that it can't move. So I'm going to draw this. I'm going to make a little box here. Okay, and at one end it's closed. That means that there's going to be a node at that end that can't move. And if it's open, it can move a lot. So we're going to have an antinode at that end. So it's going to look something like this. Okay, it's going to have no amplitude at the closed end and a maximum amplitude at the open end. Okay, and this is the fundamental for a closed one-end resonator. Now, this is how woodwind instruments work. Like a clarinet. With clarinet, you have a reed at one end, and you pinch the reed so that it can't vibrate. So that's the closed end, and then the other end of the clarinet is the open end. So we're going to label this one the fundamental frequency, so F1, and we have to figure out the wavelength. Now, this goes from a node to an antinode. If I think about that, say on this picture, it's going from the node to the antinode. Well, that's a quarter of a wavelength. So the wavelength would equal 4 times the length of the whole thing. Now my next one, when I go up and I get to the second harmonic, okay, for the second harmonic, I have to add one more node. So I'm going to have the node at the end, and then I have to have another node, say someplace down here. And at the node, it's going to be destructive interference, so there's no amplitude. And then at this open end, it has to have a maximum in amplitude. So it's going to look like this. And then let's try and figure out the wavelength. Okay, if I look on here, this one up here, I'm basically going from a node through an antinode to a node, and then to another antinode. So I have this much of the wave. All right, and that's 3/4. So the wavelength would be 4/3 L. All right. Now, if I go from the first to the second harmonic here, I've divided by 3, so this gives me F equals 3 times the first harmonic. So actually, you don't get a second harmonic with an open end. You have the first harmonic, and then you have the third harmonic. So in closed both ends, you have a first harmonic, second harmonic, third harmonic, where you are doubling, tripling, and quadrupling the frequency. With a closed one end, like woodwinds, you get a first harmonic, you don't get a second, and then you get a third. And the next one would look like this. Okay, I have to add a node. I have a node at the end, and now I'm going to have 2 more, like so. So it's going to go like this. Like so. Here's my wavelength. And if I look at this, I can divide it up into 5 sections at every node and antinode. So it has 1, 2, 3, 4, 5 sections, and the wavelength is 4 of those. So the wavelength is going to be 4/5 L. So the frequency originally was 4L, now it's 4/5, so it's 1/5 of what it originally was. So the frequency is going to be 5 times F1. So you get a fifth harmonic. So you only get the odd harmonics on the open one end. Now, the last thing we're going to talk about with these is open on both ends. For open on both ends, this is brass instruments like trumpets. Okay? If they're going to be open on both ends, that means they have to have antinodes at the ends, and you have to have at least one node. So we're going to have one node in the middle, and we're going to have antinodes at the ends. So it's going to go like this. Okay? And now, if I think about it, I'm going from the crest of a wave to a trough. So if I think of one complete wavelength, that's the crest-to-crest distance. So I've done half a wavelength here, so the wavelength would be twice as long as the length for my fundamental. And we're going to say F is F1. So this is the first harmonic, or the fundamental. My second one, I have to add a node. So I'll have 1, 2 nodes now, and it's going to look like this. Like so. This is my second harmonic. All right. And the wavelength is equal to the length, because when I go from this crest to this crest, that's going to be a wavelength. And from here to here, I have the wavelength, so the frequency doubles. So F equals 2 times the original frequency. So brass instruments have all the harmonics, even and odd, just like the stringed instruments do.